You walk into a patent office in Bern, third floor. The clock reads 8 a.m. on a May morning in 1905. At desk number 4 sits a 26-year-old clerk earning 375 Swiss francs a month reviewing applications for electromagnetic timing devices. His hair already needs a comb. His socks do not match. In less than 24 hours, this man will crack open the universe and rewrite how humans understand time itself. But right now, he cannot sleep. He has not slept properly in weeks. Because Maxwell's equations and Newton's laws refuse to cooperate and the contradiction is driving him toward madness. His name is Albert Einstein. Nobody outside this building knows it yet. His own physics professors at Zurich Polytechnic considered him arrogant and lazy and locked him out of the library. His doctoral thesis got rejected twice. 7 universities denied him teaching positions. So he examines patents. But every electromagnetic synchronization device that crosses his desk reminds him of the problem eating him alive. If you are sitting still and you see 2 clocks showing noon at the same instant, are they really simultaneous? What if you are moving? What if you are moving toward one clock and away from the other? Does noon even mean the same thing? The evening before, this May morning, Einstein walked home along the Ari River with his closest friend, Michel Besso. They had worked together at the patent office since 1904. Besso was an engineer, quiet, thoughtful, the only human Einstein trusted enough to voice the storm in his head. For nearly a year, Einstein had been spinning his wheels on the same impossible contradiction. The principle of relativity said, the laws of physics must look identical, whether you're standing still or moving at constant velocity. Galileo proved this in 1632. Newton built mechanics on it, but James Clerk Maxwell's equations describing electricity and magnetism seemed to violate this sacred rule. Maxwell's equations predicted that electromagnetic waves travel at exactly 186,000 miles per second. Not relative to anything, just that speed, always. If you chase a light beam at half its speed, you should measure it moving away from you at half speed. That is what Newtonian physics demands, but Maxwell's math said no. Light travels at 186,000 miles per second regardless of how fast you move toward it or away from it. This should be impossible. Yet experiments kept confirming it. Einstein had obsessed over this since age 16 when he imagined chasing beside a light beam traveling through space. If you could match its speed and ride alongside it, you should see the light frozen next to you like a surfer matching a wave. But Maxwell's equations said a stationary electromagnetic field cannot exist. The contradiction paralyzed him for nearly 10 years. He tried modifying Maxwell's equations, failed. He tried modifying Newton's mechanics, failed. He tried emission theories where light speed depends on the source, failed. Nothing worked. The math refused to bend. Then there was the magnet and conductor problem. Einstein described this in the opening paragraph of the paper he would write 5 weeks from now. Imagine a magnet and a wire conductor. If you move the magnet past the wire, you generate an electric current in the wire. Maxwell's theory explains this by saying the moving magnet creates an electric field, and that field drives electrons through the wire. Simple. But now flip the scenario. Hold the magnet still and move the wire. You get the exact same current in the wire, identical. But Maxwell's theory gives a completely different explanation. Now there is no electric field. Instead, the wire moves through the magnetic field, and the Lorentz force pushes electrons through the wire. 2 completely different mechanisms producing the exact same observable result, depending solely on whether you consider the magnet or the wire to be moving. This asymmetry violated everything Einstein believed about physics. The current in the wire does not care which object you declare to be moving. Only the relative motion between magnet and wire matters. The observable phenomenon should have one explanation, not 2. But Maxwell's equations, as understood in 1905, drew a sharp distinction between these cases. One required an electric field with energy. The other required only a magnetic field. Different energy content in the system, depending on your perspective. Impossible. On that May evening, walking beside the R, Einstein laid out the entire contradiction to Besso. Again, they had discussed this dozens of times. Newtonian mechanics and Maxwell's electrodynamics were the 2 unshakable pillars of physics. One had to be wrong, but which one? And what would replace it? Einstein said later that the germ of special relativity was already present in that paradox of racing a light beam. He knew the solution had to involve reconsidering the nature of time itself. But how? If you value documented physics history like this, subscribe because it is the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual using sources from John Norton's detailed reconstruction at the University of Pittsburgh's Einstein Papers Archive, published in 2022, and Peter Gallison's Einstein's Clocks and Poincaré's Maps, from 2003 which traced the exact patent applications Einstein reviewed daily. Now back to the information. Einstein returned home to Kramgasse 49, second floor. 2 rooms. His wife Mileva Maric was there with their 1-year-old son, Hans Albert. Mileva had been a physics student with Einstein at Zurich Polytechnic. She scored the top mark of 5 in applied physics, while he got only 1. They married in January 1903 against his family's furious objections. His mother called Mileva too old, too foreign, too intellectual. By 1905, Mileva had abandoned her scientific ambitions. She handled the domestic work, cooked, cleaned, cared for the baby. But friends reported seeing them work together in the evenings at the same table, late into the night, both with papers and calculations spread between them. Whether Mileva contributed mathematical work to Einstein's theories remains intensely debated. No contemporary documentary evidence proves co-authorship. Einstein's acknowledgments in his papers never mention her. Only Besso appears thanked by name. But Mileva told her father during a visit to Serbia in 1905 that they finished important work that would make Albert world famous. She used the pronoun we, make of that which you will. That night, Einstein could not rest. His mind kept circling. He thought about the patent applications he reviewed daily, dozens of devices for synchronizing distant clocks using electrical signals sent at light speed. Railroad coordination required precise time across cities. Telegraph networks needed synchronized clocks. These were practical engineering problems. But they were also the theoretical problem. If you want 2 clocks separated by distance to show the same time, how do you verify they are simultaneous? You send a light signal from clock A to clock B, but light takes time to travel. So when you see clock B reading noon, that reading already happened in the past, you have to correct for the signal delay. Fine. But what if clock B is moving away from you, or toward you? Does that change simultaneity? Einstein stared at the ceiling. Kramgasse. 49 had thick walls but thin windows. Street sounds drifted up, footsteps, distant voices, church bells marking the hours. The Bernzeitglocke clock tower a few blocks away chimed through the night. 1 strike, 2, 3, 4. Einstein turned these questions over and over. All our judgments involving time are judgments of simultaneous events. When you say a train arrives at 7 o'clock, you mean the pointing of your watch hand to 7 and the arrival of the train happens simultaneously. But how do you know 2 events are simultaneous if they happen at different places? He thought about an observer standing on a train platform. Lightning strikes 2 points on the tracks, point A and point B. If the light from both strikes reaches the observer's eyes at the same instant, and the observer stands exactly midway between the 2 points, then the strikes were simultaneous. The math works. But now imagine an observer on a moving train. The train travels from point A toward point B. Lightning strikes both points when the train is halfway between them. The observer on the train is moving toward the light coming from point B, and away from the light coming from point A. So the observer on the train sees the light from point B first. From the train observer's perspective, the strike at B happened before the strike at A. Which observer is right? Both? That is the answer that Einstein could not yet grasp, but that hovered just beyond his reach. Simultaneity is not absolute. It depends on your state of motion. 2 events that appear simultaneous to one observer do not appear simultaneous to another observer moving relative to the first. There is no universal now shared by all observers. Time itself is relative to your frame of reference. But Einstein had not yet made this leap. That May night, he lay awake, knowing the answer involved time, knowing it involved simultaneity, but unable to see how. He had been circling this problem for 7 years. Since December 1901, he told Mileva he was working on the electrodynamics of moving bodies. Professor Alfred Kleiner at Zurich advised him to publish his ideas, but the ideas did not cohere. They kept fragmenting against the same contradictions. The hours passed. Einstein drifted into shallow sleep, then woke again. His mind would not stop. Morning came. Thursday, another 6-day work week at the patent office. 10 hours a day reviewing applications. He dressed, left the apartment at 7:45, walked the familiar route through Bern's old city, Kramgasse to Marktgasse to Bundesgasse. The Swiss Federal Office for Intellectual Property occupied the 3rd floor of the Postal and Telegraph building. Einstein climbed the stairs, entered the office. Friedrich Haller, the director, earned 8,000 francs annually. Einstein earned 4,500 after his promotion to technical expert 2nd class in March 1905. When Haller told him about the raise, Einstein asked what he should do with all that money. His sense of humor persisted even through exhaustion. Einstein sat at his desk. Patent applications waited. An electromagnetic dynamo design, a method for coordinating factory clocks, technical drawings, specifications, claims. He could process most applications in 2 or 3 hours. His quick comprehension and combinative thinking made the work easy. That left time. Time to think. Time to run thought experiments in his head while his hands moved through the paperwork. This is what Einstein meant when he called the patent office his worldly cloister. The peace and material security gave him freedom to think without academic pressure to publish superficial results to advance a career. The morning passed. Einstein worked, but his mind kept returning to the contradictions. Light speed constant, principle of relativity, simultaneity, time. How did these fit together? Lunch came. Einstein often ate alone or with Besso. They would walk, talk. Einstein would voice his latest thoughts. Besso would listen, ask questions, offer the occasional insight. Besso was not a great physicist, but he was the perfect sounding board. Einstein said later he could not have found a better one in all of Europe. That afternoon, the pieces started moving in Einstein's mind. Not clearly yet, not coherently, but something shifted. He thought about simultaneity again. Not as an absolute fact about the universe, but as a human judgment dependent on comparing events. 2 events are simultaneous, if observers using clocks and light signals judge them to be so. But different observers in different states of motion might use the same procedures and reach different conclusions, both using valid methods, both getting different answers. What if simultaneity itself is relative? What if there is no absolute time coordinate that all observers share? What if each observer moving at constant velocity has their own equally valid time? The Newtonian assumption was that time flows uniformly and absolutely independent of anything else. Newton wrote this explicitly in his Principia in 1687. Absolute true and mathematical time of itself and by its own nature flows uniformly without relation to anything external. That was dogma. No physicist questioned it, but what if Newton was wrong? Einstein left the patent office at 6 p.m. He walked through Bern. May, evening, warm, the sky still light. His feet knew the route home, but his mind was elsewhere. Somewhere between the office and Kramgasse 49, the critical insight crystallized. Simultaneity is not absolute. It is relative to the observer's frame of reference. If you accept this, everything else follows. Time must be relative, space must be relative. The speed of light can remain constant in all frames because time and space measurements themselves adjust to preserve that constancy. When Einstein reached Besso that evening, possibly at Besso's home, possibly in the street, possibly at a cafe, the accounts vary, he could barely contain himself. They talked for hours. Einstein laid out his realization. Simultaneity is relative. Time is not absolute. Clocks moving relative to each other do not agree on which events happen at the same instant. This single insight resolved everything. The magnet and conductor problem dissolved. No more asymmetry. Magnetic and electric fields are not separate phenomena. They are different manifestations of a single electromagnetic field, and which aspect you observe depends on your state of motion. Maxwell's equations remain intact. The principle of relativity holds. Light speed stays constant. All the contradictions vanish. Besso listened. He asked questions. He helped Einstein work through implications. This is why Einstein would thank only Besso in the paper. Not his wife, not his professors, not other colleagues, only Michel Besso. Because Besso stood beside him during this final push and asked the right questions at the right moments, Einstein returned home late. Mileva was asleep. Hans Albert was asleep. Einstein sat at the small table in their apartment. He did not sleep. He could not sleep. His mind raced too fast. He began working out the mathematics. If simultaneity is relative, then time coordinates must transform between moving reference frames. How? He needed a mathematical relationship connecting time in one frame to time in another frame, moving at constant velocity relative to the first. The answer involved the speed of light, because light speed remains constant. The time it takes light to travel from point A to point B depends on your frame of reference. When an observer moving with point B sees a different time interval than an observer moving with point A, the transformation equations had to preserve the constancy of light speed. Einstein worked through the algebra. It was not difficult. Mostly simple calculus, nothing beyond what he learned at Zurich, but it required seeing the problem correctly. Once you accept that time is relative, the math falls into place. The night passed. Einstein filled pages. The basic structure emerged. 2 postulates. First, the principle of relativity. The laws of physics have the same form in all inertial reference frames. Second, the constancy of light speed. Light propagates through empty space at speed c independent of the motion of the source. These 2 postulates seemed contradictory under Newtonian assumptions, but if you abandon absolute time, they become compatible. They require it. From these postulates, Einstein could derive transformation equations. If system K is at rest, and system K moves with velocity of v relative to k, then coordinates and time in the two systems relate through specific formulas. These formulas would later be called the Lorentz transformations, because Hendrik Lorentz had published similar equations in 1895 and 1904, but Lorentz derived them differently. Lorentz tried to save the ether concept by treating the transformed coordinates as mathematical artifacts. Einstein took them seriously as real physical coordinates, measured by real clocks and rulers in the moving frame. This difference in interpretation was everything. Einstein worked through the consequences. Moving clocks run slower than stationary clocks. The time interval measured in the moving frame is longer than the same interval measured in the stationary frame. This is time dilation. Also, moving objects contract along their direction of motion. A ruler moving at velocity measures shorter than the same ruler at rest. This is length contraction. Both effects depend on velocity divided by light speed. At everyday speeds like walking or even flying in aircraft, these effects are negligibly small. But as velocity approaches light speed, the effects become dramatic. At light speed itself, time dilation becomes infinite. Length contraction becomes total. This means nothing with mass can reach light speed. Light speed is a cosmic speed limit. Morning arrived Friday. Einstein had been awake for over 30 hours, but he felt electric. Everything made sense now. The contradictions that tortured him for 7 years evaporated. He left the apartment early, met Besso before work. The conversation historians remember happened then. Einstein greeted Besso with 4 words: "Thank you. I have completely solved the problem." Besso stared at him. Einstein explained, "An analysis of the concept of time was my solution. Time cannot be absolutely defined. There is an inseparable relation between time and signal velocity. Simultaneity is relative. From there, everything follows." Besso asked questions. How does this affect Maxwell's equations? They remain unchanged. The equations transform in exactly the way needed to preserve the constancy of light speed. What about the magnet and conductor problem? The asymmetry disappears. Both scenarios describe the same physical situation viewed from different reference frames. In one frame, you see an electric field. In another frame, you see a magnetic force. Both are correct descriptions of the same electromagnetic interaction. What about mass and energy? Einstein had not worked that out yet, but he sensed a connection. If mass increases with velocity, then kinetic energy is somehow being converted into mass. Energy and mass must be equivalent forms of something deeper. They reached the patent office, climbed the stairs, started the workday. But Einstein could barely focus on patents. His mind kept racing ahead. He needed to write this down, formally, completely. Submit it for publication. 5 weeks. He would give himself 5 weeks to write the paper. In those 5 weeks, Einstein would work through all the implications: moving clocks, contracting lengths, addition of velocities, relativistic Doppler effect, transformation of electromagnetic fields, everything that follows from abandoning absolute time and taking the principle of relativity seriously. If you value documented physics and science history like this, subscribe, because it is the best way to support our work. Also comment from which city you are hearing this from. This script is researched and factual using sources from the Annalen der Physik volume 17 and published September 1905, where Einstein's paper appeared, and from detailed historical reconstructions in Michael Janssen and Christoph Lanner's Cambridge Companion to Einstein, published 2014, analyzing Einstein's path to special relativity. Now back to the information. The 5 weeks that followed were a blur. Einstein worked at the patent office 8 hours daily, then came home and worked on the paper. Mileva saw him consumed by it. He checked and rechecked calculations, worked through examples, made sure the mathematics held together. The paper he produced was titled "On the Electrodynamics of Moving Bodies," 31 pages. He submitted it on June 30th, 1905 to the Annalen der Physik. It was received and stamped at the journal that same day. The paper opened with the magnet and conductor problem. Einstein described the asymmetry that troubled him. Then he stated his purpose: to develop a simple and consistent theory of the electrodynamics of moving bodies based on Maxwell's electrodynamics and the principle of relativity. He introduced his 2 postulates. The laws of physics are the same in all inertial frames. Light speed is constant regardless of source motion. Then he defined simultaneity. 2 events are simultaneous in a given reference frame if light signals sent from both events reach an observer midway between them at the same instant. This definition is operationally clear. It tells you how to measure simultaneity using clocks and light signals, but it immediately implies that simultaneity is relative because observers in different frames will not agree. From this foundation, Einstein derived the transformation equations for coordinates and time between moving frames. Then he showed how electromagnetic fields transform. Then he applied the theory to specific problems. Aberration of starlight. Doppler effect. The paper mentioned only 5 scientists by name: Isaac Newton, James Clerk Maxwell, Heinrich Hertz, Christian Doppler, Hendrik Lorentz. No other references, no citations to contemporary work. This was unusual. But Einstein worked in isolation. At a patent office, not a university, he did not have easy access to journals. He relied on books and his own thinking. This isolation was partly why he could make the leap. He was not embedded in the academic consensus. He was free to question assumptions everyone else accepted. The paper acknowledged only Michel Besso. In the final paragraph, Einstein wrote these words: "In conclusion, I wish to say that in working at the problem here, dealt with I have had the loyal assistance of my friend and colleague M. Besso, and that I am indebted to him for several valuable suggestions." That was it. 1 sentence. But it guaranteed Besso a footnote in history. Without Besso serving as sounding board in those critical days, Einstein might have struggled longer, might have given up, might have spiraled into frustration. But Besso was there at the right moment, asking the right questions, letting Einstein voice the chaos in his mind until clarity emerged. The paper was published in Annalen der Physik, Volume 17, Issue 10 in September 1905. Page numbers 891 through 921. Einstein was 26 years old. Still a patent clerk, still unknown, but that volume, 17, became legendary. Einstein published 5 papers in it that year. March issue covered the photoelectric effect, proposing that light consists of discrete quanta of energy. This idea was so revolutionary that even after Einstein won the Nobel Prize in 1921 for this work, many physicists still rejected it. May issue covered Brownian motion, proving atoms exist by explaining the random jiggling of microscopic particles suspended in liquid. June issue was the relativity paper. September issue followed up with a short paper showing that mass and energy are equivalent. If a body emits energy as radiation, its mass decreases by an amount equal to the energy divided by light speed squared. This gave us E equals mc squared, though Einstein did not write it in exactly that form until later. 1905 became known as Einstein's Annus Mirabilis, his miracle year. 4 groundbreaking papers. Each one alone would have secured his reputation. Together, they rewrote physics. But when the papers appeared, almost nobody noticed. Physics journals received countless submissions. Most were wrong or trivial. Even major results could sit unread for months or years. Einstein's papers looked like just more articles in an obscure journal by an unknown author making strange claims. Gradually, word spread. Max Planck in Berlin read the relativity paper with interest. In July 1906, Planck wrote to Einstein. Other physicists began paying attention. Max von Laue visited Einstein in Bern in 1906, expecting to find a professor, and was surprised to meet a patent clerk. But recognition came slowly. Einstein continued working at the patent office until October 1909. By then, he finally received an academic position. Associate professor at University of Zurich, his salary was 4,500 Swiss francs, the same as his patent office salary. But now he could teach, research, join the academic community. Over the next decade, special relativity gradually gained acceptance. Experiments confirmed time dilation. The Ives-Stilwell experiment in 1938 directly measured relativistic Doppler shift and found perfect agreement with Einstein's predictions. The Rossi-Hall experiment in 1941 measured the lifetime of cosmic ray muons traveling at relativistic speeds and showed their decay time stretched exactly as special relativity predicted. Today, special relativity is tested thousands of times daily. Every particle accelerator depends on it. GPS satellites must correct for relativistic time dilation, or navigation would fail within minutes. The theory is not speculation. It is engineering fact. But go back to that May evening in 1905, before the paper, before the mathematics, before the recognition. Einstein walks home along the Aar River. He has worked at the patent office for 3 years, earned just enough money to support his small family, faced rejection from universities, struggled in obscurity, but he carries in his mind a question that will not let him rest. What is time? How do we measure simultaneity? Why does light always travel at the same speed? That night he cannot sleep. The pieces swirl. Magnetism, electricity, light, motion, time, they refuse to fit together under the old assumptions. So maybe the assumptions are wrong. Maybe time itself is not what Newton said. Maybe simultaneity is not absolute. Maybe different observers experience time differently depending on their motion. The next day he talks to Besso. and suddenly the pieces lock into place. The insight arrives not as a slow realization, but as a flash. Simultaneity is relative. That is the key. Everything else follows from that single recognition. Time transforms between reference frames, space transforms, but light speed stays constant. The contradictions dissolve, the universe makes sense again. Einstein returns home, stays awake through the night, works through the mathematics. By morning, he has solved it. The problem that consumed 7 years evaporates in 24 hours of focused clarity. This is how breakthroughs happen. Not gradually, not by accumulation, but by sudden insight after long preparation. You circle the problem until you find the right angle. Then everything becomes obvious. 5 weeks later, Einstein submits the paper. 3 months later, it appears in print. 70 years later, physicists still use his equations to design experiments and build technology. GPS, particle accelerators, nuclear reactors. All depend on understanding that time is relative, that mass and energy are equivalent, that space and time form a unified four-dimensional structure. We navigate by Einstein's insights. We power cities with them. We probe the cosmos with them. But none of this was inevitable. Hendrik Lorentz had the transformation equations in 1904. Henri Poincaré discussed relativity principles in proper time in 1905. If Einstein had not made the leap, someone else might have within a few years. Maybe. But Einstein saw it first. He saw it because he was willing to abandon absolute time. He saw it because he took Maxwell's equations and the principle of relativity seriously even when they seemed to contradict. He saw it because he thought about what simultaneity actually means operationally. And he saw it because on one May evening in Bern talking to Michel Besso, the insight finally crystallized. The archive at the Einstein Papers Project at the Hebrew University of Jerusalem contains over 80,000 documents from Einstein's life. Letters, manuscripts, calculations, personal notes. Historians have combed through them, reconstructing the path to special relativity. What did Einstein know when? Which papers did he read? Who influenced his thinking? The record remains incomplete. Key documents are missing. Einstein's recollections, decades later, were sometimes vague or contradictory, but the essential story is clear. 7 years of struggle, one breakthrough moment, 5 weeks of intense work, then a paper that changed physics forever. In Einstein's later life, he worked on general relativity, extending special relativity to include gravity and acceleration. That took 8 more years and produced his greatest achievement: the realization that gravity is not a force but the curvature of space-time itself. Massive objects bend space-time around them, planets orbit, not because gravity pulls them, but because they follow straight paths through curved space. This prediction was confirmed in 1919 when Arthur Eddington measured starlight bending around the sun during a solar eclipse. The deflection matched Einstein's calculation. That made Einstein world famous overnight. But general relativity built on special relativity. Without the 1905 breakthrough, the 1915 theory would not exist. After Einstein died in 1955, scientists examined his brain looking for anatomical clues to genius. They found slightly unusual structure in some regions. Whether this meant anything remains debated. Genius is not located in brain folds. It emerges from how someone thinks. Einstein thought by visualization, by thought experiments, by imagining what riding alongside a light beam would look like, by considering how observers moving at different speeds would measure the same events, by taking physics seriously enough to question its deepest assumptions. On the night before his breakthrough, Einstein could not have known what was about to happen. He knew he was close. The problem had consumed him for years. He had tried every conventional approach. None worked. So maybe the problem required an unconventional answer. Maybe time itself was not what everyone assumed. That thought terrified and thrilled him. If he was right, he would overturn 2 centuries of physics. If he was wrong, he would waste years chasing a dead end. But the contradictions demanded resolution, and Einstein could not let them go. So he stayed awake, paced, thought, talked to Besso, walked home, worked through the night. And in those 24 hours before the breakthrough, he carried in his mind all the pieces that would soon fall into place. Maxwell's equations, the principle of relativity, the constancy of light speed, the magnet and conductor problem, the nature of simultaneity, the operational definition of time, the transformation equations between moving frames. All these elements were present. They just needed the right organizing principle. Simultaneity is relative. That was the principle. Once Einstein saw it clearly, the rest followed within hours. The patent office in Bern still stands. Kramgasse 49 is now the Einstein House Museum. You can visit the second-floor apartment where Einstein lived with Mileva and Hans Albert. The rooms are small, simple furniture, a desk, a bed, a kitchen table. Standing there, you can almost see Einstein at the table late at night, papers, spread out calculations, scrawled in his quick handwriting, while Mileva sleeps, and the baby stirs, and the Zitgloga clock tower counts the hours, and Einstein's mind races toward the insight that will arrive when the sun comes up. In 2005, the World Year of Physics marked the centennial of Einstein's miracle year. Conferences, exhibitions, documentaries, renewed examination of the 1905 papers. Historians and physicists debated details. But the fundamental achievement remained undisputed. In 5 months, from March to September 1905, a 26-year-old patent clerk published 4 papers that transformed our understanding of light matter, energy, space, and time. That such revolutionary work came from outside academia, from someone without a doctoral degree, without a university position, without access to laboratories or advanced equipment, testifies to the power of pure thought. Einstein had no experimental apparatus except thought experiments, no expensive detectors, no teams of assistants, just a desk, a pencil, and a mind willing to question everything. The story could have ended differently. If Einstein had not met Besso, if the patent office had rejected his application, if Mileva had demanded more of his time and attention, if he had gotten an academic position earlier and felt pressure to publish conventional results, if he had given up after 6 years of failure, any of these would have delayed or prevented the breakthrough. But the circumstances aligned. The patent office job provided financial security without academic pressure. Besso provided the perfect sounding board. Mileva, whether she contributed calculations or simply gave him space and time at the table, enabled his work. The electromagnetic synchronization patents crossing his desk kept the problem of simultaneity front of mind, and Einstein's stubborn refusal to accept contradictions drove him to keep searching even after conventional paths failed. What remains is the moment itself, that May evening and the night that followed. Einstein exhausted from lack of sleep, mind-racing pulse elevated walking home from his conversation with Besso, knowing he has finally seen it. Simultaneity is relative. The words echo in his head. He wants to run but forces himself to walk. People pass on Kramgasse. Shopkeepers closing for the day. Families heading to dinner. None of them know that the young man hurrying past is about to rewrite physics. He climbs the stairs to the second floor, enters the apartment, sits at the table, begins working through the mathematics. And by morning, when he meets Besso again, Einstein can say the 4 words that mark the end of his long struggle. Thank you. I have completely solved the problem. This moment separates before from after. Before Einstein time was absolute universal, flowing uniformly for all observers. After Einstein time became relative, dependent on reference frame, woven together with space into a 4-dimensional continuum. Before Einstein, mass and energy were separate conserved quantities. After Einstein, they became equivalent interconvertible forms of the same underlying reality. Before Einstein, physics contained contradictions that brilliant minds accepted as mysteries beyond resolution. After Einstein, those contradictions dissolved into a simpler, deeper, more beautiful description of nature. The archive at Boston University contains detailed reconstructions by a historian of science, John Norton, documenting Einstein's pathway to special relativity. Norton analyzed which problems Einstein confronted, which solutions he attempted, which ideas he borrowed from predecessors like Lorentz and Poincaré, and which insights were uniquely his. The analysis published in 2014 in the Cambridge Companion to Einstein shows Einstein's route was not direct. He explored emission theories, he tried to modify Maxwell's equations, he struggled with field transformation laws. He even briefly considered abandoning the principle of relativity, but he kept returning to the contradictions, and he kept trying to resolve them. This persistence through years of failure was itself remarkable. Peter Gallison's 2003 book, Einstein's Clocks and Poincaré's Maps, connects Einstein's theoretical breakthrough to his daily work reviewing clock synchronization patents. Gallison argues the patents were not just background distraction, but active influence. Einstein thought about time coordination problems every day at the patent office. How to synchronize distant clocks using electromagnetic signals. How to account for signal propagation delay. How to define simultaneity operationally rather than metaphysically. These practical engineering concerns shaped the theoretical question. The patent work trained Einstein to think about time as something measured by physical procedures, not as an abstract Newtonian absolute. Whether this connection between patent work and theoretical insight is causal or coincidental remains debated. But the correlation is striking. Einstein examined electromagnetic timing patents. He developed a theory where time depends on electromagnetic signal velocity. The paper he wrote used operational definitions. 2 events are simultaneous. If observers using light signals measure them to be so, this matches how patent applications described clock synchronization. Send signal, measure delay, correct for propagation time. Define simultaneity relative to signal exchange. Einstein took engineering procedures seriously as physics. The consequences extended far beyond 1905. Special relativity led to general relativity. General relativity predicted black holes, neutron stars, gravitational waves, the expansion of the universe. These predictions took decades to confirm, but they all followed from taking seriously the idea that space and time are not fixed containers, but dynamic entities shaped by matter and energy. The universe Einstein described was stranger and richer than anyone imagined. Massive objects warp space-time. Time runs slower in gravitational fields. Gravitational waves ripple across the cosmos at light speed. In February 2016, the LIGO Observatory detected gravitational waves from colliding black holes 1.3 billion light-years away. The signal matched Einstein's equations precisely. This was 101 years after he published general relativity in 1915. But it all started on one May evening in Bern, with a patent clerk who could not sleep, who had been thinking about light and time for 7 years, who was willing to question Newton, who had a friend who listened, who made the leap. Simultaneity is relative. Time is not absolute. Different observers in different states of motion measure time differently. Both are correct. There's no universal now. Accept this, and everything follows. Reject this, and physics remains contradictory. Einstein chose to accept it. The choice required courage. Overturning 200 years of Newtonian mechanics was not done casually. But the contradictions demanded resolution, and Einstein trusted mathematics. If the math worked, if the equations gave correct predictions, then the physical interpretation must be right, even if it violated intuition. Time dilation sounds impossible. But if experiments confirm it, then time really does dilate. Length contraction sounds absurd. But if the math requires it, then lengths really do contract. Absolute simultaneity seems obvious. But if taking simultaneity as relative resolves contradictions, then simultaneity really is relative. This willingness to follow mathematics past intuition defined Einstein's approach. It would guide him through general relativity, where he learned enough differential geometry to describe curved spacetime. It would frustrate him later when quantum mechanics produced mathematics that worked beautifully, but seemed to describe a probabilistic universe without definite reality. Einstein never made peace with quantum mechanics. He spent his final decades searching for a unified field theory that would restore determinism. He failed, but his earlier successes came from trusting the mathematics even when it led somewhere strange. 24 hours before his breakthrough, Einstein did not know he would succeed. He knew he was close. He knew simultaneity was the key, but he had not yet made the final connection. That would come the next day after talking to Besso. Then it would come fast. Insight, recognition, clarity, the kind of sudden understanding that feels like remembering something you always knew. Of course, simultaneity is relative. How could it be otherwise? Why did it take 7 years to see something so obvious? This feeling of obviousness after breakthrough is common. Before the insight, the problem seems impossibly hard. After the insight, it seems trivially simple. The difficulty was not in the mathematics. The difficulty was in questioning the right assumption. Once you realize time is not absolute, the rest is undergraduate calculus. But realizing time is not absolute when everyone, including Newton himself, says it is absolute requires a special kind of stubbornness. Einstein had that stubbornness. It made him difficult as a student. His professors resented his arrogance. But that same quality let him question what others accepted. And in May 1905, it let him crack open the universe. The work did not end with the breakthrough. 5 weeks of intense calculation followed. Writing the paper, checking every equation, making sure the theory was complete and consistent, then submission, then waiting, then publication, then years more waiting for recognition. But the hard part was those 24 hours before. The struggle, the exhaustion, the frustration of knowing you are close, but not quite seeing it, then walking home, talking to Besso, thinking about simultaneity, going home, staying awake, working through the night, and finally, seeing it clearly enough to say to Besso the next morning the problem is completely solved. In the basement of the Swiss Federal Institute of Intellectual Property in Bern, historians later found records of patents Einstein examined. Electromagnetic dynamos, telegraph synchronization systems, electric clocks, methods for coordinating time across rail networks, the actual applications with Einstein's handwriting in the margins. He processed applications efficiently. Most took him 2 to 3 hours, but some left marks, notes, questions, ideas sparked by technical diagrams. These documents show Einstein engaging deeply with practical electromagnetic problems. At the same time, he was wrestling with theoretical contradictions in Maxwell's electrodynamics. Theory and practice intertwined. This interplay between practical engineering and pure theory characterized 1905. The photoelectric effect paper explained how metals emit electrons when struck by light. This was a practical phenomenon with technological applications, but explaining it required proposing that light consists of discrete quanta. Pure theory, revolutionary theory. The Brownian motion paper analyzed microscopic particles jiggling in liquid. This was a practical observation made by botanists, but explaining it required demonstrating atoms exist. Pure theory, profound implications. The relativity paper started with magnet and conductor, practical electromagnetic induction, but resolving it required reconceiving time itself. Pure theory, universe-altering theory. Einstein moved fluidly between practical and theoretical. He did not see them as separate domains. This integration reflected his patent office experience. Patents describe practical inventions, but evaluating them requires understanding physical principles. Does this device violate conservation of energy? Does this mechanism actually work as claimed? Answering these questions demands theoretical insight. Einstein developed the ability to move from practical specifics to general principles and back. This skill served him well in 1905 when he needed to connect abstract ideas about space-time to concrete observations about magnets and conductors. The final detail worth noting is what happened after. Einstein submitted the relativity paper on June 30th, 5 weeks after his breakthrough, but his work did not stop. In September, he submitted a second paper, 3 pages, a footnote to the relativity paper. It showed that if you accept special relativity, mass and energy must be equivalent. A body's energy content equals its mass times light speed squared. E equals mc squared, though Einstein wrote it as m equals E divided by c squared in the original paper. This was the most famous equation in science. It meant tiny amounts of mass contain enormous energy. 1 kilogram of mass is equivalent to 90 quadrillion joules, enough energy to power a city for weeks. This prediction would eventually lead to nuclear power and nuclear weapons. But in September 1905, it was just mathematics. Pure consequence of taking special relativity seriously. Einstein saw this connection within weeks of his breakthrough. The train of thought continued. Accept simultaneity is relative, accept time dilation and length contraction. Work through the implications. You discover mass increases with velocity. Moving objects become more massive. At light speed, mass becomes infinite. Therefore, nothing with mass can reach light speed. But if mass increases with velocity, where does the extra mass come from? From kinetic energy being converted into mass. Therefore, mass and energy are interchangeable. Therefore, E equals mc squared. All of this followed from that May insight about simultaneity, one realization cascading into others. This is how physics advances, not by isolated discoveries, but by chains of reasoning where each step enables the next. In the century since 1905, special relativity has been tested in countless ways. Time dilation measured with atomic clocks flown on aircraft. Length contraction observed in particle accelerators, where fast-moving particles decay more slowly than predicted by classical physics. Mass-energy equivalence demonstrated in nuclear reactions, where mass converts to energy with stunning precision. Every test confirms Einstein's equations. Every new technology based on relativity works exactly as predicted. GPS, particle physics, synchrotron radiation. All depend on taking special relativity seriously, not as philosophical speculation, but as engineering reality. Yet the moment of discovery remains human, a man in his 20s, unable to sleep, consumed by contradictions, talking to a friend, walking home, sitting at a table, while working through the night, no supercomputers, no research teams, no billion-dollar experiments, just thought. Pure, concentrated thought about the nature of time and space and light, and in 24 hours the contradictions dissolved. The universe made sense in a new way, and physics would never be the same. That moment in May 1905 connects to today every time you use GPS navigation. The satellites orbiting Earth travel at speeds where relativistic effects matter. Time on the satellites runs faster than time on the ground by 38 microseconds per day. If this correction were not applied, GPS would drift by miles within hours. Your phone knows where you are because engineers programmed Einstein's equations into the satellites. The young patent clerk, staying awake through the night thinking about simultaneity, made your navigation possible. His insight became infrastructure. His thought experiment became technology. The story ends, not with Einstein famous, but with Einstein exhausted and satisfied, having finally solved the problem. 5 weeks later, he will mail the paper. Months later, it will appear in print, Years later, physicists will recognize its importance. Decades later, it will reshape human understanding of space-time and reality. But right now, in these 24 hours before the breakthrough, Einstein does not know any of that. He knows only that he cannot sleep, that the contradictions torment him, that he is close, that Besso helps him think, and that when morning comes, he will greet his friend with gratitude and the simple statement that he has completely solved the problem. And he will mean it,